Today we're going to look at compound interest, and I want to explain the difference between simple and compound interest. We're going to do that in Microsoft Excel. From there we can derive a formula and then look at some examples. Alright, so let's get started. Alright, so here's the situation. We're going to invest $100, that's my principal, at a rate at 10%. And interest gets accrued once a month. And I'm going to show the difference between simple interest and compound interest. So the way simple interest works, and you can see how I have the formula here in the formula bar. If you don't know Excel, that's not too much to worry about. But the way simple interest works is that every month I'm going to tack on another 10% of the principal. So after 1 month, I now have $110. And if I keep going, the second month, I tack on another $10, $120, and so on and so on. All right. So after 11 months, this account's gone from 100 to 210, which is pretty good. Okay, now with compound interest, it's not exactly like that. Let me show you the first month. 110. See, well, okay, that's actually the same thing. Not a big deal, because what we're going to do from now on isn't, and you can see the formula in the formula bar. You don't have to worry about that. We'll explain it more in math terms in a little bit. But the way compound interest works is that it tacks on interest, not just the principal, but it tacks on the interest to the account. So now for the next month, I'm not going to just calculate 10% of 100. I'm calculating 10% of 110. So that's going to be $121. And look, that is a little bit different now in simple interest, but only by $1. So what happens as this goes on, I keep tacking on interest to what was in the account, not just the initial principal. And look at that. By the 11th month, I have outgrown simple interest by $75. Right? I'm at $285. So how does this work? Again, it's tacking on interest not just to the initial principal, but to what is in the account currently. So each month I'm adding 10%, and that 10% is actually growing each month, if that makes sense. All right, let me show you the formula, how this works, and we'll look at some examples. Okay, so now from Excel we can see that actually compound interest grows at a quicker rate. And it's like this, if you remember. To find your future value, which we call A, you take your principal, and then you keep multiplying this rate, and we're going to use R over N, N being the number of times we compound. So in our example, we used months. It can be something else. And we multiply that by itself, the number of times we compound it. So we can call that K. And then more formally, usually we know that K is going to be a number of years. So we, instead of saying K, we say NT. And then here, T is years. N is compounds a year. All right. R is your interest rate. P is what you initially invest, your principal, and then A is your future amount. Alright, so let's look at some examples, and it's pretty straightforward, but what's interesting here is that this is an application of exponential equations. Look, you have something to a variable power, NT power. So for example, Jeff invests $10,000 in an account that's earning 4.5% annual interest compounded quarterly. Okay, what is the value of the account after 3.5 years? And so one thing I didn't mention here is when we have a formula like this, we're really thinking of A as a function of time, a function of T. So T could be your variable, and notice here we're plugging in T to be 3.5 years. Okay, so T is 3.5. So I take my formula that I just had, and I just need to plug in 3.5 in for T, and my other appropriate values as well. And let's try to figure out what those other values are. Okay, so if I'm looking through this, I can see that I have $10,000 that I invest. That's my principal. So I know I have $10,000 for P. I have an interest rate of 4.5%. So R is not 4.5. Remember, you have to write this. That's 4.5%, which is going to be, we have 1 plus R is 0.045. All right, that's 4.5%. Now, what about N? N is the number of compounds. And notice we said here we're compounding quarterly. N is the number of compounds per year. So quarterly, that means you have 4 compounds per year. So N is 4. And so here in my exponent, I have 4 times 3.5. And that's my future value after 3.5 years. I just have to carefully plug this into a calculator and make sure you do that. Make sure you can get this value. If you do plug it in carefully, you should get around $11,000 or let's say $11,695.52. So that would be the amount that you grew in 3.5 years. And think about this. I mean, Jeff just put $10,000 in, which is pretty good. But did he do anything after that? No, he just let it sit there for 3.5 years. And in doing that, he gained almost $1,700. That's a pretty good return on an investment, I'd say. And so there is our future value. I hope this makes sense. It's just plugging in the numbers and typing it in the calculator correctly. Let's look at another example. So this time, in example 2, 9 months after depositing $520 in a monthly compounded savings account, Pierce checks his balance to find that he has $528.84. What was the interest rate? That's what he can't remember, and he can't find it anywhere. What was our interest rate? Okay, so this time we're still using the same formula, A equals P1 plus R over N to the NT power. And here again, I'm using A as a function of time, so T is my variable. And so notice the 520 is what we invested. So P here I know is going to be 520. Okay, what else do we know? We know this $528. That's going to be the future balance. So I know that number as well, 528.84. And then I think I know some of this other stuff. We don't know the interest rate, right? That's what we're trying to find. So R is N, but we do know that it compounded monthly. So that means then that N is 12. And I think we also know time, don't we? 9 months. Now here's where we have to be careful. We're not talking about 9 years, right? So time is not 9. Time is 9 out of 12, right? 9 months out of 12 months. That's how you convert it to years. And that kind of makes our math a little bit easier, right? Because here the 12 is going to cancel out. And once I divide both sides of this equation by 520, I should get 1.017 equals 1 plus R over 12 to the 9th power. Okay, so now I just need to figure out this thing out for R. I can do that by taking the 9th root of both sides. So the 9th root of 1.017, which is approximately 1.001875, is approximately this 1 plus R over 12. So from this point, it's a linear equation, right? I subtract 1 from both sides to get R over 12, and then multiply both sides by 12 to get R equals, be careful, this is where you have to put it in a calculator, you get approximately 0.0225. Okay, so if you're going to write that as a percentage, R is about 2.25%. Okay, so this is the basics of compound interest. If you understand compound interest, it will change your life. In particular, you'll learn how to avoid credit cards because they have high interest rates. You'll learn how to shop around for good interest rates for savings accounts and investments, mutual funds, etc. This is kind of the doorway into finance. And notice it's just an application of exponential equations or exponential functions. If you have any questions on this, guys, I'd be glad to help you. And thanks for watching.